Hi, we already introduced the sequences. We talked about arithmetic and geometric sequences. Now we will talk about the limit of a sequence. What's the concept of limit? I have a question to ask. If we have a wall in here and somebody standing in here and he's walking towards the wall, the question is, if each hour, so each 1 hour, this guy will make one step. Okay, the steps can be of different sizes. So if each 1 hour he makes one step, is there a way of making steps such that he will continue to make steps his whole life without never reaching the wall? Is this possible? Or if he will continue to make steps, it's for sure that he will reach the wall? That's the question. In fact, the answer is yes, he can make steps according to a following strategy without never reaching the wall. Let's say, for example, let's consider that the distance from here to here is 10 meters. So if the first step would be 5 meters, which is half of the distance between the person and the wall, and then this is the first step. Then the second step, I will make it in yellow. So this is the first step. Then the second will be half of the remaining distance. So it's 2.5. And then the third step will be half of the remaining distance. And then half of the remaining distance. And then half of the remaining distance. So he will continue to make steps and he will never reach the wall. So there is a strategy of making steps and approaching something, which is the wall in here, without never reaching the wall. And this concept is very important. It's due to the fact that you can always find real numbers between the position where you are standing and the wall. I mean that this distance, the remaining distance, is always a real number that you can divide by 2 to find another real number that represents half the distance, and so on. So this gives us an idea about infinity. So infinity is something very large. It's something that you can always go forward towards it, but you will never reach it. So here you can make an infinite number of steps without never reaching the wall. That's why we can have a sequence of numbers, in this case the steps, that will approach a given number, which is the wall, without never reaching the wall. Let's say, for example, a sequence of numbers like 1, 1 over 2, 1 over 3, 1 over 4, etc., 1 over n, etc. So this sequence can be represented by the general term un equal 1 over n, right? So these numbers are decreasing towards 0, but they are never reaching 0, and they can continue forever. Okay, so the concept of approaching something without never reaching it exists. But the thing now is the following. These numbers are approaching 0, right? So if you have the axis in here, 0 in here, 1 is here, so 1 over 2 is here, 1 over 3 is like here, 1 over 4 is here, etc. And you are approaching 0. The thing is, you are approaching 0, right? But you are also approaching -1. I mean that 1, the distance between 1 and -1 is 2. And then between half and -1 is 1.5. And then between 1 over 3 and -1, 1 over 4 and -1, the distance is always decreasing, right, between the numbers and -1. So you are approaching -1. So what's the real difference between -1 and 0? The difference is that you are approaching both numbers, right? But even if you go very far, if you go to n, when you choose n very, very, very far, you will never be able to have a distance between your number and -1 less than 1. I mean, even if you take n very high, your 1 minus n will be in here somewhere before 0. So the distance between this, your number, and minus 1 will be always greater than 1. So that's right, you are approaching minus 1, but there is a distance that will always separate you from minus 1. But from 0, it's not the case. From 0, you will approach 0, we say, indefinitely. What does it mean, indefinitely? It means that if you take 0 and here on the axis, and you take whatever step from 0 to the right, okay, I will show it as a big step, but it can be a very tiny small step to the right. You will always find n very large, such that n is closer. Okay, you can reduce your step now. If you reduce your step, you make a small step, and you can find n very large, such that 1 over n is even closer. So the difference between 0 and minus 1, or 0 and any other number less than 0, is that 0 is the only number that you are approaching indefinitely. Whatever step you make from 0 to the right, you will always find a number from the sequence 1 over n that will be closer to 0. That's why this number, 0, I will call it the limit of the sequence un, n, un is the sequence defined by 1 over n, when n becomes very large, so when n tends to plus infinity. Okay, so this is how I define the limit. Let's make it more mathematical. I will define the limit as being a number such that even if you make a tiny interval around this number, so even if you make a tiny interval around 0, you will always find an element of the sequence inside, closer to 0. Okay? So I will repeat this definition. A limit of a sequence is a number that even if you take a very small interval around this number, you will always find an element of the sequence inside this interval, so closer to the limit. Okay? But this definition still lacks something. In fact, imagine your sequence is doing this, like un equal minus 1 to the power n over n plus minus 1 to the power n. So in this case, u0 will be minus 1 to the power 0, it's 1, sorry, no u0 because you have over n, we start by u1. So it's minus 1 over 1 minus 1, so it's minus 2. u2 will be equal to 1 over 2 plus 1, which is 3 over 2. Then u3 would be equal to minus 1 over 3 minus 1, which is equal to minus 5 over 3. Then u4 is 1 over 4 plus 1, which is 5 over 4. Then u5 is minus 1 over 5 minus 1, which is minus 6 over 5. u6 is equal to 1 over 6 plus 1, which is 7 over 6. So if we place these numbers, I have 0 in here, minus 1 in here, 1 in here. So the first number is minus 2. So we start by the first number, minus 2. This is u1. And then u2 is equal to 3 over 2. So it's in here, u2. u3 is equal to minus 5 over 3. So it's like 1 point something. So it's closer to minus 1. It's in here, u2. u3 is u3. This is u3. Then u4 is 5 over 4. So it's somewhere in here, u4. u5 it's in here, u6 is in here, etc. So we can see that our numbers from this side, they are approaching minus 1, and from this side they are approaching 1. So it's true that if you take any tiny interval around 1, you will always find a number of the sequence inside the interval for n large enough. And if you take any tiny interval around -1, also you will find a term of the sequence for n large enough inside the interval. So which means that 1 and -1 are both limits according to the definition I already stated when I said that a limit is a point such that if you take an interval around it, even if it's a very, very small interval, you will always find an element of the sequence inside, closer to the number. So does that mean that these 2 points are 2 limits? We have a problem in here, because we have to differentiate between the sequences that have such behavior, so they are approaching, the elements are approaching 2 numbers, and the sequences that have the first behavior in here, where all the numbers are approaching, or all the elements of the sequence are approaching the same number. So we will stick to the first one. We will say that a limit is the first case. It's when all the elements of the sequence are approaching 1 number. Okay, so I will redefine the limit by saying that a limit of a sequence is a number such that if you take a tiny small interval around this number, you will not only have one element for n large enough inside the interval, you will have all the elements of the sequence from a given index n, starting a given index n, you will have all the elements of the sequence inside. And this is true for 0, you see. So for 0, if you take a very tiny interval in here, if you find n large enough such that 1 over n is inside, then all the elements coming after this element 1 over n for the specified n, they will be inside because they are closer to 0. So from starting a given index n, all the remaining elements will be inside. And this is the definition of the limit. So according to this definition, we don't have this case. We don't have the case where elements are approaching 2 numbers, because if I take this definition and I want to apply it in this second example, so in here, it's true that if you take a tiny interval around 1, you will find n large enough such that un for this n is inside. But as you can see, the un afterwards, so un plus 1 will be in here, because this sequence is alternating. It's having positive values when n is even and negative values when n is odd. So it will be always like this. So any un you will find inside in here, the element after it will be in here. So you will not have that starting a given point or a given index and all the elements are inside one interval. Okay, so I will try to write this down mathematically. So I will say, if you take an interval, I will recall the definition and write it mathematically. If you take a very small interval, even if it's very, very, very small, around the limit, or what you want to prove that it's a limit. So if you take a very small interval, it means that if you take a positive number epsilon and you check the small interval, which is the limit or supposedly limit minus epsilon and the limit plus epsilon, if you take this interval, which is an interval around the limit. Okay, so if you take a positive epsilon, any epsilon you take, so for all epsilon, because for any epsilon you take, no problem, even if it's very, very small, you will always find an element, or starting a given point, all the elements will be inside this interval. So you can find a starting point that I will call n0, an index that belongs to n, such that for all the elements after the one given by un0, for all n greater than n0, the elements un belong to the interval L minus epsilon L plus epsilon. So this is what we call the definition of the limit. Okay, so for any epsilon you take positive, even if it's very, very small, there exists a rank or an index n0 such that any n greater than n0, so all the elements after un0, they will be very close to the limit, closer than epsilon. I mean, the distance between them and the limit is less than epsilon. Un belongs to L minus epsilon, L plus epsilon, which is the interval around the limit. So this is how we define the limit of a sequence. Let L be a finite number in R, of course, real number. We say that the sequence un tends to L as n tends to infinity, and it's always as n tends to infinity. We have no other option because n belongs to big N natural number and it goes to infinity. That's the only way it can go. As n tends to infinity, or we can say also that it has a limit L when n tends to infinity, if and only if, for all epsilon positive, you can find a given index, here I called it big N, such that for any natural number which is greater than n, you have un minus L less than epsilon, and this is equivalent to un minus L between epsilon and minus epsilon, which means that un is less than epsilon plus L and L minus epsilon. Okay, so this is the same definition I wrote earlier. So you should really memorize this definition. We will use it in the proofs. It's a very important definition and we'll use it also in the coming chapter. Let me point out something in here, that it's very important to write the instructions in this order. I mean, for all epsilon positive means that you can choose any number, any positive number, even if it's very, very small. Okay, let me say you choose epsilon equal 0.1. Okay, then you will take the interval L minus 0.1, L plus 0.1, right? And you will be able to find a rank n such that any un after this u big N, after this rank n, will be inside the interval in here, right? Now, if you take these instructions in this order, it means that your choice of big N is depending on the choice of epsilon. Because if you take, for example, the sequence that I already stated, like un equal 1 over n, okay? So if you take epsilon equals 0.1, it means that the interval will be 0 plus 0.1, 0 minus 0.1, right? So then, what is this magical index? I will call it in here n0 now, such that for any n greater than n0, un is inside this interval. So if you take n0 equal 10, then un0 will be 1 over 10, which is inside this interval, right? And any other un with n greater than n0, so un, if you take u11, it's 1 over 11, u12, it's 1 over 12, etc. They are all inside the interval, right? Now if you take a smaller epsilon, like 0.01, what would happen? Then the 1 over 10 will not work anymore, because 1 over 10 will not be inside the interval 0 minus 0.01 and 0 plus 0.01. Okay, now in this case you have to find a greater n0 that satisfy the property. So now your n0 will be 100, because from n0 equal 100, any un with n greater than 100 will be inside the interval. So the choice of n0 or big N in here, this number depends on the choice of epsilon always. That's why we write the instructions in this order for all epsilon positive. So first you choose epsilon, then I will be able to find a rank n0, an index n0, such that for any n greater than n0 you have the property. So the choice of n0 depends on the choice of epsilon. Okay, so let us see how this shows up on a figure if I want to represent the sequence on a figure. So as I told you before, here we have the indices, and here we have the y-axis where we show the values of un, but the values doesn't matter really now. That's why I removed them, so to show you only the behavior of the numbers of the sequence. Okay, so you have, this is u0 in here, and then this is u1, and this is in here u2, and etc. So this is a sequence that is going a bit up always. It's going upwards, and then it's approaching the red line, which is L. Okay, so let's say that L is a given number on the y-axis, and the sequence is approaching this number, and you can see that if you take an interval around L, which is L minus epsilon from here to here, okay, L minus epsilon and L plus epsilon, from a given point, from a given index, this one in here, so it's from 9 upwards, all the elements that are after u9 will be inside the interval that you chose, L minus epsilon 1, L plus epsilon 1. And if you choose a smaller interval, L minus epsilon 2, L plus epsilon 2, you will find a greater index, which is 25 in this case, such that from 25 and upwards, all the elements will be inside this interval around the limit. Okay, so this is a representation of what I tried to tell you. And in this case, the sequence is going upwards. We can take a sequence that is alternating around the limit. So it has values below and values above. Like here it's u0, u1, u3, u4 below, and then, sorry, u0, u1, u2, u3 is in here, and u4 is in here. So u3 is above the limit L, and u4 is below the limit L, or the line L. And then you are always like alternating or staying sometimes at the same side, etc. But it's also verifying the limit concept, because if you take an interval L minus epsilon 1, L plus epsilon 1, you can find that from the index 13 and upwards, all the elements are inside L minus epsilon 1, L plus epsilon 1. So this is epsilon 1 here. Okay, and if you take a smaller interval, L minus epsilon 2, L plus epsilon 2, you will find that from the index 18 or even 17, all the elements are inside L minus epsilon 2, L plus epsilon 2. So it can be like this. An example of this sequence would be like 1 plus minus 1 power n over n. You see, this is a nice sequence, because for n equal 1, u1 is equal to 1 minus 1 over n. So 1 minus 1, it's 0. And then u2 will be 1 plus 1 over 2, so 3 over 2. And then u3, it's 1 minus 1 over 3. u4, it's 1 plus 1 over 4, and etc. So there are numbers alternating around 1 and getting closer to 1 from both sides. Okay, this is an example of the sequence more regular even. Now, when L is not a limit, L is not a limit when the sequence will approach L, but not indefinitely, as the example I gave you in the sequence un equal 1 over n, when I said it's approaching minus 1, but minus 1 is not a limit because we are not approaching minus 1 indefinitely. We have always a constant distance that will separate the elements from minus 1, and this is the representation. You see, so the sequence in here, it's approaching something in here, but it's definitely not the L that is in red. So L in this case, we are approaching L, but not indefinitely. So L in this case is not a limit. So we call a sequence convergent when un tends to a finite limit L, finite, not infinity, as tends to plus infinity. The sequence is divergent when it is not convergent. Okay, so the sequence is divergent when it's, for example, going to plus infinity, like this one, the elements are growing and not reaching a limit where they can stop, so they are growing to plus infinity. So here you have, this is a red line, but it's not a limit, it's just in here. Or if the elements you see in here, so this is u0, u1, u2, u3, so this is a sequence approaching two numbers. This is the first one and a second one in here. So in this case also, this sequence is divergent because it's not approaching a given element, which is a one element, as I explained earlier. So these two sequences are divergent. Now, before going further, let me define let me write down a definition of a limit equal to plus infinity. So we say that a sequence has a limit equal to plus infinity, but it's still a divergent sequence because the limit is not finite. So it has a limit equal to plus infinity if and only if you take a number a positive, even if it's very, very large, you can find an index n such that from this index and so on upwards, all the elements are greater than a. It means that if you choose a like 1 million, you will find an index n such that all the remaining elements are above 1 million. Okay, it means that you can take a very, very large, you will always find an index where all the elements afterwards are above this number, so they are going to plus infinity. And also the same when it's going to minus infinity, but we take un less than minus a, which means that they are going to minus infinity. So now a little remark is that if you take a sequence that is convergent, let's say this sequence in here, okay, this sequence is convergent to a limit in here, and if you remove some terms, like you remove the first I don't know, 20 terms, the remaining sequence will stay convergent. So if you remove a finite number of terms from a sequence, the remaining are the infinite number of terms. They will be always converging to the same limit. So the nature of a sequence, whether it's convergent or divergent, will remain unchanged if a finite number of the terms of the sequence is removed.